Okay, so in this video, we're going to be looking at finding the surface area of revolution for a parametric curve. And so here's my example, my parametric function. X of t is t cubed plus 1, and y of t is t squared plus 1. And if we look at the graph, we have this section of the graph that falls, in this case, under the x-axis. And it's nice and well contained. And in fact, you can see from the graph that it's intersecting the x-axis at 0 and 2. And so that's where we're going to do our integration. We just have to find out where those intersections are occurring. And they're going to be when, in fact, this is the y function, when the y function is equal to 0. Actually, I had a typo here that I fixed. This is t squared minus 1, not t squared plus 1. And so if you set this equal to 0, you can easily see that the t values we're going to need are going to be plus and minus 1. So we're going to integrate this section of the graph, and we can go ahead and draw on it. This section right here. And we're going to find the surface area of revolution when we revolve that either around the x-axis or the y-axis. Now, the general formula for the surface area of revolution in parametric form is going to look like this. We're going to integrate from some values of t. There's going to be a radius function, and then there's going to be an arc length function. And the arc length component is going to be based on our parametric curves. So we're going to need to take the derivative of each component and then square them under the radical. And what's going to change when we revolve around the x-axis or the y-axis is precisely what this function out front of this is. If we rotate around the x-axis, then r of t will be, the radius will be depending on the y function right here, because the radius as we rotate around the x-axis in this vertical orientation like that, then the radius of each of our slices is going to depend on the height of that y function. So then that would become y around the x-axis. And if we rotate around the y-axis, then the radius is now the distance to the point on the curve that we're rotating. And so that just becomes x of t. So we have these two versions around the x-axis. We simply replace r of t with y, and around the y-axis, we would simply replace r of t with x of t. So as long as we keep in mind which axis we're rotating around, then we just basically have to worry about this general function. There's a radius function, and then it just is either going to be x or y, depending on which axis we're rotating. Now, if we go and we look at our particular function, we're going to need to calculate which axis we're rotating around. I'll do the example for both of them, and then we're going to need to calculate our derivatives in order to plug them into our function. So let's go ahead and find our derivatives. So x prime of t, since our original function was t cubed plus 1. This is going to be 3t squared, and y prime of t, since that was originally t squared minus 1, this is going to be 2t. And then our arc length component, this piece right here, is going to be 9t to the fourth plus 4t squared. And we can actually simplify this a little bit by bringing a t squared out. And then the square root of t squared is just t. And then if we're going to rotate around the x-axis, then our function would look, our integral would look like the following. 2 pi is out front, and we're going to integrate between -1 and 1. Our y function, because we're going around the x-axis, our y function was t squared minus 1. And then our arc length component, we already simplified to t times the square root of 9t squared plus 4 dt. And we can simplify that a little bit. That's going to be t cubed times the square root of, let's actually do it this way, t cubed minus t times the square root of 9t squared plus 4. Now, the issue that we're going to run into when we actually try to do this integration, if we were to try to do it by hand, then the 1 here with the t on it and the radical, that's just going to be a straight up substitution. But when we do the t cubed times the radical, then we're going to have to do integration by parts on that term. And then we'll be able to do straight substitution. So sometimes these rotation problems, like with the solids of revolution, if you don't choose your functions very, very, very carefully, you end up having these very complicated integrals that you have to solve. I'm going to just leave this one here. We can do integration on it in another video. But basically, that's what you're going to end up doing. The t cubed tends to becomes a integration by parts with borrowing, because you need to steal a t in order to integrate the radical. And then the t by the radical is just a regular substitution. So it is not insane, it's not crazy, but it is something that you do have to work through a little bit. So I'm just going to leave the integral set up like this. If we wanted to rotate around the y-axis, then our integral will become 2 pi from -1 to 1. And then our x function is going to go out front, and that was t cubed plus 1. And then our radical, our arc length piece, t times our 9t squared plus 4. Now, when I do this distributing, wrong integral. I'm going to end up with t to the fourth plus t and the radical. And this one is going to be not just integration by parts. This one is going to require trig substitution. Again, if you just do the t term times the 9t squared plus 4, then this part is just u substitution. But t to the fourth times the radical, in this case, it's not integration by parts. You could do one step of integration by parts, but then you would get stuck. And so what you would end up having to do really is you would have to do trig substitution in order to do this integration with a tangent substitution. One alternative, of course, is to simply evaluate it numerically, depending on, the needs of your instructor, then that may be adequate to just throw it in your calculator and do the integration that way